So let's get started, everyone. So welcome back. So I'm glad you're all enjoying being back in person. So in talking to all your neighbors, so there's kind of some rumors spreading about some. So I haven't heard any. So COVID spreading in this. So class, but I've heard COVID spreading. Maybe starting to spread in so some of the lower level classes. I don't think anything's been put all online, but just kind of so everything's aware. You know, stuff's been on Zoom, and most people have been so staying out of the classroom. So I wouldn't be so totally concerned, but I hope you know, if you think you might have been exposed, you can watch on so the lecture on Zoom. Otherwise, I'm glad everyone's back in the classroom. Hopefully, we'll be able to stay here the whole semester. I think I heard an announcement that hopefully the new boosters that would be effective against preventing infection for the current strain might be available as early as next week. So that might be something to look forward to. So let's just quickly go where we are in the schedule. We are, you've probably seen as of Tuesday, so homework 1 is posted. You can so start working on that. Probably after this lecture, you should be able to do everything on there. Is definitely after the lecture on Tuesday. So you can start working the homework, not due until September 13th, so you still have some time for that. So we are supposed to, we're kind of at the end of the review of probabilities, but you've probably also seen Bayes' rule before, but we'll get into things like maximum likelihood estimates. So my goal today is to kind of start to show you some new material and give you some insight into how it's going to link to the rest of the semester. My goal is to get through a simple example about how to compute the maximum likelihood estimate of a single point, of a single one-dimensional value. And you know, it's not going to be too surprising what the right thing to do is, but we're going to start with the probability and kind of derive what the right thing to do is. And probably again, because I kind of wanted to get to a good end of an example to tie stuff together, the lecture today will probably be going at a kind of a faster pace material. And then we'll kind of go over a more advanced version of it in the lecture next week, Tuesday. So if it goes a little bit faster, we'll kind of redo it all again on Tuesday with a bit more kind of some like a more formal version of it. So you'll kind of see this again. All right. So the topic will be Bayes' rule. So one more thing from the syllabus. So I will do my best to try and respect your your chosen name and your chosen pronouns. I figured out this week how to put my pronouns on Canvas. That's why you may have started seeing them showing up. You don't so you don't have to if you don't want to. My pronouns are he, him, and his. So kind of in outside of class, I'm pretty flexible. So what you call me, what you refer to me as in class, I will try and go by Prof. Phillips. So this isn't kind of the reason why I would like you to call me this instead is there's kind of an effort from kind of all of the faculty in in the School of Computing to kind of have like a more uniform way of so the way people address faculty. I don't think this so much addresses really affects me so much, but I want to kind of have a more uniform standard for. There are some of my colleagues where I think it's more important to call them this way. So I'd like to be consistent in this course. So if you have any kind of questions or concerns about these sort of issues about names and so forth, so there are resources you can find here. So just say one more thing. So one kind of interesting way where these sort of issues have like affected problems in data science. There's one project I worked on over the last few years where we are trying to. One thing you do with data is you often, we'll see in this course, you map it to a representation. So you can have a representation of my name or of parts of language. One interesting kind of development recently is you would take text and you would map it to some sort of representation. As we'll see, this will often be as some sort of vector. And for a long time, this vector representation was something that was designed by someone. And a recent change in natural language processing, a lot of other things, was this was used machine learning to learn the representation of the vector, right? And this allowed it to be, there's lots of advantages I won't go into, but it worked much better if you learned what the right representation was than for downstream machine learning. And so it turned out for things that affected captured information about gender of individuals, you could do a very good job of learning representations if they were male or female, but for some part of the population, they would prefer to kind of have their pronouns as something else. And that was a very big challenge in learning these representations because there's a lot less data on this, especially since we're training from the web, and the web dates back to when this was much less common to use pronouns other than say he and she, right? So this was a modern challenge within kind of in data science. We don't have a good solution for yet, I would say, where if you want to learn representations for pronouns other than the more traditional he and she sort of pronouns, this kind of learning that representation is still kind of a challenge. Okay, great. So I want to start a bit with with a small review, okay, of what we are talking with probability for, and this because and then they'll get into just a few definitions that we missed that will actually be important over the next couple of lectures. So this is I'm going to start with this probability table where there were this was about a friend of mine in college who had a pattern of the way he would wear his clothes. He would store all of his clothes in a big pile on the floor of his dorm room, and he would choose kind of random pants and shirts from the pile every day. What was kind of amusing about this is at the end of the day, when he was taking his stuff off, he would also put it back in the pile. And then when the whole pile got kind of smelly enough, then he'd just he would take everything to the laundry altogether. So it was he didn't want to fold his clothes. So what was interesting about that is that it means that if he wore pants on the day before, it doesn't affect the next day's so probability of wearing the same pants, right? So I don't have to worry about how this evolved, in between his cycles of cleaning the clothes. So he either has pants or his shirt. These were the only two things that were kind of relevance to his outfit. And so you could say his pants were either blue or white, and his shirts were either green, red, or blue, right? And so there's a probability table we can put in here. So 0.3, this would be the probability of a green shirt and so blue pants, right? 0.1, probably red shirt and blue pants. 0.2, probably blue pants and a blue shirt. 0.05, white pants, green shirt. 0.2, red pants or red shirt and white pants, and 0.15, right, blue shirt and white pants. Okay, so these should all add up to 1. It's a probability. And then there are certain kind of definitions you can read off this table. And so one is if we have, so often we'll say the probability of P equals blue and S equals green, right? And that is this number here. That's one element in the table. We'll write an intersection of those two events, or maybe you just have a comma if they're both true. Another way of approaching this is conditional probability, right? So let's say the conditional probability that the shirt was red. So you can say the probability of the pants equals blue, given that the shirt was equal to red, right? And this was equal to the probability that the pants equals blue and the shirt was equal to red, divided by the probability that the shirt was equal to red. Remember, the conditional way to think about that was that I'm conditioning on the shirt being red, so now my sample space is restricted onto this column, right? So I'm dividing by that, and so the answer here is going to be 0.3 over 0.2. And I want to put this union up here at the top, right? Oh yeah. So this is, no, that's not right. Okay, so it's 0. Right. The total probability that the shirt is equal to red is the sum of these two, right? So that's going to be 0.3 here. It's the probability that the shirt is red, and then the intersection that the pants are blue, given that it's red, is going to be 0.1 divided by 0.3. So it's 1/3 is the sort of probability here. Okay, what's going on here at the bottom? This is the probability that the shirt was red. I can write this for the other ones as well. The probability that the shirt was green, this is 0.35, and the probability the shirt was blue is also 0.35. If you notice 0.3, that this kind of row here, this is what's called the marginal probability. This is the probability. This is the probability of just the shirt. Okay, so this would be the marginal probability. This is, you just take the columns, or you can do this with the rows. You just add up along the columns. So this is kind of like I'm writing in the margin, or if I've marginalized out the choice of the pants. If you marginalize a person, means you're kind of ignoring that person, right? So if I'm marginalizing out the probability of the pants, I'm kind of ignoring this aspect of the probability, and I'm just getting the total here. Notice that these add up to 1 also, right? So this is also a perfectly fine probability distribution. Okay. Okay. So we talked about most of this. What we didn't talk about was that if you have, instead of a discrete probability, remember we could define for a random variable x, we had a PDF. This has the property that for all values in a sample space, f of x, this integrates to 1, and I have f of x of omega is always going to be in 0 up to infinity. If I have 2 random variables, x, y, then I can write the joint probability of x and y. And I wrote this as lowercase x and lowercase y, right? And this is actually not a probability. If it's a continuous random variable, we would call this a likelihood. Often we'll say maybe more specifically what I refer to as the likelihood with respect to data a little bit later in this lecture. But I can define conditional, and this also is the property. It integrates to 1, and the values are between 0 and infinity. But we can define conditional and marginal distributions with respect to these as well. So I can go to the marginal, right? So I can write f of x from this distribution for a value x. And what I would do is I would integrate over y on the relevant sample space of f of x, y, so dy, right? Okay, so I can marginalize out all the values of y. So it's the same thing as before. Instead of taking a sum over the column, I'm integrating over this choice of y instead. Okay, so this is how I marginalize this out. And this is where I have multiple kind of a probability or a likelihood or density function that depended on multiple random variables. I want to get the effect just one random variable by marginalizing out this value y. And I can also then define the conditional random variable. So I can say that, what's the notation I want to use here? F of x given y, say it would be x. So often you would say y equals, let's say y 1, right? And so this would be f of xy, which I can evaluate at x, so comma y1, the value that's true, divided by f of y, the value at this value y1. Okay, and I could have calculated this guy, which is only dependent on one of these, on just y as a marginal. I would have written down the marginal for y instead of x, right? So this would actually be f of y y1 would be integral over x in its domain, f of x. So f of x in so y1 here. Okay, so I can define the marginals in the same way on these continuous random variables, and we will yeah, the notation is there's a lot of stuff going on in the notation, but the important thing is to realize this idea of marginalizing and conditionaling that is very intuitive on tables. You can generalize this to these conditional random variables as well. All right. So, okay, great. All right, so let's talk about, Bayes' rule. Okay, so the first thing about, the first rule about Bayes' rule is that the apostrophe comes after the S here. So it's named after Thomas Bayes, and it's his rule. So I mean, it's something that's true about probability, but the apostrophe comes after the S. Okay, and this is an important kind of fact about probability, and we'll actually derive this. And we're going to have two events, M and D, and the events will correspond with so I'll use M and D here because these will think about M as the model and D as the data. Okay, and so this will be important. Where this whole course is going to be about how to build models of data, and so this will be the kind of the core for talking about the probabilities of these models and data. Okay, and so the rule is just an equation about conditional probability. It's the probability of a model given some data is equal to the probability of the data, given the model, times the probability of the model divided by the probability of the data. Okay, or it could be other events. We'll go through a few examples in this lecture, right? Okay, so this is just a kind of an equation that that you can derive. Okay, put a box around this equation. It's pretty important. All right, so the reason why this is interesting is we can often, this is something that we can this term, the probability of the data given the model, is something we that we can compute. Okay, we can often compute that quantity. We can sometimes compute this property, the probability of the model. Sometimes we just assume that we know this. Sometimes we can ignore this. And we're mostly going to ignore this term down here, the probability of the data. We have observed the data, so the data exists. It doesn't so much matter what the probability is of the data is going to be. So we'll see this, but this is just some intuition. We would like the left-hand side. We'd like to know the probability of a model. We'd like to find something like the most likely model, the highest probability model given the data that we have observed. And we can compute probably data given the model. Those two are not the same. Okay, but we can convert between them using this rule. And so that's why this rule is kind of really important in kind of understand how to think about the probabilistic nature of kind of building a model sort of representation. Okay, but before we go into more kind of detail and examples, let me just kind of explain why this is true. If you remember that the probability of the model given a data, we can write just the definition here is the probability of the model intersect the data, so they're both true. divided by the probability of so the data, right? So this is just the definition of the conditional probability, right? So this is just what the definition is. And so I can actually, what's useful is to write that just some algebra. The probability of the model intersect the data is then equal to the probability of the model given the data times the probability of the data. And I can also write that the probability of the model intersect the data is equal to, well, the probability of the data intersect the model. Intersection, it's so commutative, right? And so this is equal by the same sort of definition, probability of the data given the model times the probability of the model. Now I can set these two expressions equal to each other, right? Because the left-hand side is the same here. Okay, so I can say probability of the model given the data times the probability of the data is equal to probability of the data given the model times the probability of the model. And now I just take this guy and divide through the right-hand side. Okay, so from the definition of conditional probability, you can derive this rule, right? So there's hopefully nothing kind of controversial about this equality. Yeah.
You compute the data in the model, but you don't know the model.
Yeah. So that's the thing. We don't know what the model is, and we're going to try and find the most likely model. Okay, so we'll go through some examples to see this. What I said before is just a preview of what we'll see over this lecture and the next one. Okay, and then this will underlie the foundation of the rest of the course. But I'll need to do a number of transformations first. So we'll walk through these. Okay, yeah. So there's, you may have heard about, I remember when I was in college, there was this big kind of, I was at there was a very Bayesian based statistics department, and I had heard a lot about these controversy between frequentist and Bayesian views of the world, and there were statisticians that would be very kind of heated arguments against each other. They're not arguing whether this is true or not. This Bayes rule is true. That frequentist versus Bayesian perspective is about how this is used, right, within modeling. And we're going to kind of walk through a Bayesian perspective. There's nothing controversial about that. There's some controversy about kind of if this is the right way to assume it, or if there's other right, and we aren't going to get into that part. So if you're concerned about the frequentist versus Bayesian, nothing we're going to talk about is controversial. We're going to talk about we're just going to derive some formulations from the Bayesian perspective. Okay. All right. So let's just, yeah. Maybe I'll do a very simple example here. Let's say a probability table. Okay, and I just want to do. Okay, so one thing I'm going to be doing, sometimes we'll talk about the events. If there are events, and they're binary events, either it's true or it's not true. We're going to see more kind of things that aren't just true or not true, but we'll often just say the probability of D being true. This is similar. Then it's it could be a random variable instead of event. They're kind of mapping to 1, 0 in the truth values. But so but we don't necessarily need to say probability, this is the same as the probability of D equals 1. I'll just write as a shorthand as the probability of D being true. Then if this is the case, we can calculate that the probability of the model given the data by, oh, well, let me fill in values in the table here. 0.5, 0.2, 0.05, right? So let's calculate using Bayes' rule, probability of the model given the data, probability of, probability of the data given the model, probability of the model divided by the probability of the data. To calculate this, okay, well now I need to calculate the probability of the data, so given the model, right? And remember, this is the probability of the data intersect probably the model divided by the probability of the the model, right? And this was probably the data and the model. This is 0.25, and the probability of just the model being true, I need the marginal probability, that's 0.45 here. So this is divided by 0.45, right? I'll just leave it as this fraction for now. Now we have the probability of, I also need the probability of the model. So this one, so this is 0.25 divided by 0.45. This with probability of the model, I already calculated 0.45. And the probability of data, that's 0.75, the marginal distribution on the top row here. So this is 0.75. Okay, so now I multiply these two values on the top together and they cancel. So I'm going to get 0.25 divided by 0.75, and this is 1/3. Okay, so this is how I would go through a probability table with Bayes' rule. I can directly calculate this as well. I can also say the probability of the model given the data is the probability of the model and the data divided by the probability of the data, right? 0.25 divided by 0.75, 1/3. It's the same thing, right? Okay, good. Okay, good. We saw the numbers are the same thing, but this seems like, why did we go through this, right? This was a harder calculation so far, right? If I have all this information, I don't need to use Bayes' rule. It's just convincing you that it's true, it holds up. I didn't do anything special. I'm just rewriting it in terms of these things. In this case, the probability of the data given the model was probably the most painful calculation here. But in general, this won't always be the case. Okay, so let me, okay, so let's go through another kind of a longer example of where this would be useful. And this is the cracked, windshield example. Okay, so the kind of the story here is that you bought a car and so the windshield cracked. Okay, so you have a random variable or an event. Yeah, so you have an event that the windshield, it's cracked on your car and you're angry about this. You want to figure out, why did the windshield crack? Who's at fault for the windshield cracking? Okay, and you start looking into this and you realize that the windshield for your car came from some factory, but you don't know which one. So there are three. There are three factories. A, B, and C, and you want to know which one is the most likely one to have made your your windshield, so you can go and complain to them. Okay. All right. So, and you find out that the factories have different. Some factories made more windshields than others, right? So if you don't, if I just look at all the windshields that were made, I find out that factory A made half the windshields. Factory B made 30%, and factory C made 20% of the windshields. Okay, so I'm saying I'm thinking maybe I'm going to complain to factory A. This is the most likely factory that made my windshield. Yeah.
You're saying that the probability that it was A is 0.5, or you're saying
yeah. So of all, I'm saying that the probability of A being the factory that made windshield is 0.5. So if I have a windshield, I want to know what factory made it. Probability is 0.5. If I look at all the windshields made, say, in the cars sold in the United States, half of them came from this factory. Okay, so I'm not incorporating anything else into here. Okay. Okay. But now I look into this and I find out, well, certain factories seem to have had more problems than others. So with the windshields cracking, in fact. And so if you look at the probability that of a factory to have that the windshield cracked, given that it came from factory A, right? So of all the windshields that came from factory A, what fraction of these cracked? Okay, you can maybe look at all the windshields and say what fraction of them cracked, and maybe this is only 1%. Okay. In practice, probably the numbers are much smaller than this, but for this example, and you can look up this for factory B. Of all the windshields they made, what factory cracked? What fraction of them cracked? So let's say 10% from factory B. And from factory C, the probability that the windshield cracked, given that it came from factory C, was 2%. Okay, so now I know, well, the windshields from factory B are much more likely to have cracked, but I also know that it's likely they're more made by factory A. So who is more likely at fault here, right? Which factory is the most likely to have made my windshield, which is cracked? Okay, so what I'd like to figure out now, if I'm given this information, I'd like to look at probability of factory A made the windshield, given that it cracked, right? This is my situation, right? And so I can write this down as the probability, right? I can use now I can write down Bayes' rule, right? So the probability that the windshield cracked, given it came from A, times the probability it came from A, divided by the probability that the windshield cracked. Okay, I haven't told you this number, and let's just kind of hold off and go through and see what we can see here. So that's 0.5, right? The probability, this is 0.01. The probability that the windshield cracked, given it came from A, 0.5. The probability it came from A, divided by the probability it cracked. Okay, so this is 0.005 divided by the probability it cracked. Now I want to compare this to the other kind of possible kind of suspect here. Is it more likely it came from B, right? This is probability that it cracked given from B. The probability it came from B divided by the probability that it's cracked, right? This is now 0.1 times 0.3 times divided by W. and this is 0.03 divided by the probability it, so correct. I could do the same thing for C, given that it cracked, and I'll skip the steps, but this will end up being 0.004 divided by. Okay, so if I just look at the right-hand side of these calculations here, I can see that it is 6 times more likely to have come from factory B than it is to come from factory A. Okay, I don't actually have the probability it came from B. I haven't worked that out. I could work this out, right? I actually know that this is a probability space. Given that it cracked, restricted to that, it must have come from one of these 3 factories. So I can actually solve for W because these should add up to 1, right? These values should add up to 1. But I don't need to do that in order to determine which is the most likely factory. It's 6 times as likely to have come from B as it is from A, and also even more likely, about something like 7 or 8 times as likely to have come from B as it to have come from C. So C is the most likely factory here. And I did this through Bayes' rule. Bayes' rule was necessary. From the information I had, this is what I could calculate, and I could drive these probabilities, which is the most likely kind of factory is that the windshield came from. Okay, yeah. Yeah, B is the most likely, right? Yeah, right. It's got the highest probability. I didn't even tell you what the probability was, but I know it's the highest. Okay, good. This makes sense. So it seems like, okay, this could actually be useful. All right. So all right. So this is kind of a mini simple version of what we're going to be doing for learning models that are kind of the basis of things like like machine learning instead. Okay. Where instead of A, B, or C, we're going to have continuous space of events instead of discrete space of events of what the model could be here. Okay. Okay. So right. So again, we're going to think about M as the as the model and D as the data, right? And we want to think of this left-hand side of Bayes' rule, right, as the probability of a model given that I've observed data. Okay, the data I'm collecting, I'm using this to try and figure out the probability of a model. And what would I like to do? I'd like to find the most likely model, right? This is the best model that fits the data in some way, but it's the most likely deriving from some kind of probabilistic view of this. Okay, there are a couple things that are going to be tricky here in how we talk about this. So what we'd like to find is there's a space. So we're going to have a sample space. This is the space of the models. Well, actually a parameterized space of the models, and we will see concrete examples of this. But now our sample space will be a set of all possible models, and we would like to find what is called some model in the space. Okay, and we want to find the one that the one that maximizes the model given the data that that we have observed. This one we will call M star, and this will be the map, the map estimate. So map, so this is the maximum the posteriori estimate. There's some, this I think comes from Greek. But this we're going to write down something, and we're going to call it the posterior. And I'll write this down next. That's where this term comes from. We'll just call it the map estimate. Write that MAP. Okay, this will be the map estimate. And what is this? We're going to say that M star is going to be the arg max. Let me just write this down and then kind of say something about it. The model from the sample space of probability of the model given the data. Okay. Okay. So you're probably familiar with a maximum sort of operator. If you have a set, you want the max returns the maximum. So element of the set. Okay. The argmax is taking the argument which causes the function to be the maximum value. Okay. So there's a function that I want to maximize, but I don't care what the value is that I maximize. I just care about the argument, the model, which maximizes this value. Okay, so I'm gonna, this is like the factory which maximize the probability that it produced my windshield given that the windshield was cracked. I care about which factory is the maximum. I don't care about the probability. Okay, this is going to be kind of, in fact, we're going to write down some continuous probability, kind of some probability distribution functions for continuous random variables and sample spaces, and we won't actually be able to talk about the probability. It's that value so much won't make sense to talk about, but the one that maximizes it will make sense. Okay, so we're going to talk about the model which maximizes this. That's our goal. Okay. Okay, and so using Bayes' rule, we can write this down as argmax of M from the set of models of probability of the data given the model, probability of the model divided by the probability of the data. Okay. And what's nice here is that the data is something that we are going to know and is fixed, right? Like the fact that my windshield was cracked. So that means that we can actually ignore this term here. I'm going to actually cross it off, right? And we're going to write arg that's equal to the arg max from the sample space of probability of the data given the model times the probability of the model. This is an inequality, right? But I do not have the numerator anymore. Okay. And that's because I'm taking the argmax. If I had taken the max and I cared about the actual value, I can't just get rid of this term, that denominator, because that would affect the actual value. But if I just care about what maximizes it, because it's the same for all the models, it doesn't depend on the choice of the model, it doesn't affect which one maximizes the function. Okay, so the maximum a posterior estimate, right? This term here, the product of the probability of the data given the model times the probability of the model is called the posterior. Okay, so those are the posterior, and this is the maximum model of this posterior function. Okay. Okay, so this is, yeah, question?
Sorry, is the probability of the model, is that like chance that the model represents reality?
Yeah, so that's going to be what's called, so the prior, right? We're going to have a prior, we have prior knowledge about something about the model. And so again, this is, we don't know what maybe there is a true model, right? But we don't know what the true model is, but maybe we say, we think it's more likely to be a simple model of some way. So we're going to put a probability on all models so that we give higher probability ones which are somehow which are going to be simple. That's a preview of what you'll eventually see. For now, the next thing we're going to do for the rest of this lecture is just like ignore the prior, in fact. Yeah.
So isn't the prior model the Bayesian?
No, it's so you can do Bayesian kind of you can do Bayesian statistics kind of so like assuming the prior on the model is just a constant. This is one modeling choice you can make, and so but you can still do. I'll talk about this probably next lecture. What you get out of the Bayesian statistics. What we're going to be doing is just looking at the maximum, the argmax of this. Bayesian statistics gets its power from actually trying to think about the probability distribution itself. But we're going to actually just take the maximum thing out, the most likely thing, and that's really not the core of where the power of Bayesian statistics comes from. I'll mention this a bit more in next lecture. Yeah. So okay, so let's see. So okay, so what we're going to do next is assume this is called the prior, and we're going to now assume that the prior is also so that the probability of the model is also a constant. No, we don't assume any model is more likely than any of the other models. Okay, so if we have a discrete number of models, we can, and say we have, n models, we can say it's equal to, like 1 over n. But if we have a continuous number of models, then we need to write down kind of a probability, either a uniform probability distribution, or if the space is infinite, then it's a little bit trickier to state specifically what the thing is we're going to do, but we're going to assume that's constant, right? And so if we assume it's constant, well, then we're going to say that m star arg max m in the space of the models, the probability of m given the data, well, that now becomes equal to arg max of the probability of the data, so given the model. Okay, this is not in general true, and I said, okay, the probability of the model given the data is not equal to the probability of the data given the model. I cannot generally interchange these, but if we assume that the prior knowledge of the model is uniform, then we are going to say the arg maxes are the same under this particular assumption. This is known as the maximum likelihood, estimate. Okay, and we'll just call this the MLE, the maximum likelihood estimate. Okay, and this object here, this guy is called the likelihood. Okay, so just the likelihood of just the likelihood of the data given the model. Okay, and so we're just going to maximize that function, and as we'll see next, this will be something we can typically write down and compute this. Okay, and so often you know, so I'm going to kind of go through a particular, yeah, we're doing okay on time. I'm going to go through a particular example in one dimension where we're going to actually be able to calculate the maximum likelihood estimate of so of a set of data here. Okay, yeah.
Going back to the windshield example, you had 3 different probabilities models for that example. How can we assume the probability of the model is constant when we're calculating this argument?
Yeah, right. So if we go back to this example, yeah. So let's say we didn't know the distribution of the windshields, like that we didn't know that factory A made half the windshields. We just didn't know anything about this. So we just didn't have that information. Or let's say that all the factories made the same number of windshields. Then that would also be a constant. Okay. Right. So in that case, then it would only depend on, then you could derive using Bayes' rule the probability that, you know, a certain factory was the most likely to have caused my cracked windshield. It would only depend on the probability that the windshield was cracked given it came from the factory, right? Because then this probability of A and probability of B would have been equal, right? So I could have also just left that as a constant at the end here. And I just have the, you know, the condition, the likelihood left. Everything else would have been constant. And to determine the most likely, I wouldn't have needed to kind of even calculated that value. Now, if I knew it, then I get more information here. Okay. So if 90% of the windshields, or if let's say 99% of the windshields came from factory A, right? Let's say I bought the car in Salt Lake City, and Albuquerque was a factory, and Boston is another one. I'm most 99% probability my car came from Albuquerque, right? The factory, because that's much closer. So then that probability would be higher, and that would actually kind of that would dominate this cost. Okay, this function here. But if I don't know that information, then I can just use this likelihood.
If we have that information, we would worry about how to
No, I'd still find the max, but if I don't know it, I assume it's equal. All right, and that's what. So sometimes you want to do that, sometimes you don't want to do that, and we'll see some examples of that. Right. So what I want to do next is go through an example where we assume that the prior is all equal, and then on Tuesday next week we'll go through another very similar example where we don't assume it's equal, and we'll see how it changes things.
So can I ask about the probability of the data? If say like we knew that like 2% of our data was fake or something, then would we have to worry about that? Like it's like we know.
Yeah, well, we would put that. Yeah, you would put that into the calculation of the probability of the data. So given the model, that'll make a little bit more sense once I kind of go through the next example. Yeah. What is the model? Yeah, so far the only example you've seen, it can mean lots of things, and I will. Yeah, actually, this is the next thing I want to. So yeah, so this is the next slide. So let me maybe answer this on the slide. Right now, the model is only one of the 3 factories, but it's going to be kind of a lot of other possible things, right? This data, let me first say the data is going to be x1 up through xn, and these are going to be, we're going to assume these are independent, so observations. Okay, and I'll give some context to this in a bit, in an example. But the model is then going to be something explaining so some structure in the data. Okay, so we're going to go through the first example we're going to go through in the rest of this lecture is where this data, it's going to be points in R1. In general, it could be d-dimensional space, but let's say it's just going to be values. Let's say I measured a bunch of heights of the people in this classroom. Okay, so they could be a bunch of values, and if there are 100 people in here, then n is 100. I have 100 data observations. It's not quite independent and you know, unbiased draws, but we'll kind of push this under the rug, at least for now. And then the model might be M might be, and we'll say it'll be the mean. What you'd like it to be is a value of the the average height. Okay, and this is the average height, typically under the assumption that it's so normally distributed. And I'll go through this in a bit more detail in the example. But we'll say, I assume I drew this data of all the heights of the people in the class, and I'm going to model this as, let's assume that there's an average height and there's a normal distribution, like we plotted on Tuesday, that describe the distribution of the heights off of this normal. And we can argue about whether this is the right model, but this is the one where the math is going to be kind of really nice, that we'll go through for now. And then we'll add other stuff onto this model throughout the semester. Okay, so this will be the same thing, the simple thing, the value of the average height. And so the model will be represented by a single parameter value. Okay, this is the example we'll go through in more detail. But let me kind of just preview some other ways that we have a data and model that we'll see throughout the rest of the semester. In the second one, we'll think about linear regression. Okay, in this case, M is going to be, let's just think about linear regression in 2 dimensions. M is going to be a line in R2, right? So we're going to have kind of an X and a Y axis, and our model is going to be a line. This will be M. And we're going to have data, which are going to be points, and we're going to assume that each data point came from this line, but had some normal noise that was added to it from the true location on the line. Okay, and we're going to find the line that fits this the best. Okay, so we have, all we observe are these data points. This is X1, X2. This all lives in 2-dimensional space. You have an X coordinate and a Y coordinate. Okay, and I want to fit a line where if I assume that the data came from the line with normal error, normal noise on top of it, what's the most likely line to fit this data? We will solve this problem later, and this fits into this paradigm. Another one we will solve is clustering. There are many formulations of clustering. We'll look at the k-means kind of formulation of this clustering. In this case, the model, instead of a single, let me first say the data will be points in RD, so d-dimensional space. I can draw in 2 dimensions, but you can think in higher dimensions. The model will be a set of points. Let's say, right? So it could be, this is M1 and M2. These are parameters. I need to describe all these points, and I assume that there's some normal error on each of these points. They could be in higher dimensions, so it's Gaussian error, and then the data is clustered around these, and it came from each of these points from this distribution. Okay, so now I need to find my model is now multiple points instead of this first example with 1 point. This will be the one way of modeling, so clustering. We'll look at k-means clustering and also a mixture of Gaussians algorithms in this class. Right, and so this work in higher dimensions as well. All right, so this is another extension of this model. Let me say a couple more. A fourth one would be, we'll talk about principal components analysis. And now, in this case, the data will be in D dimensions, and D is going to be large, and the model will be an element of Fk. This will be a k-dimensional, so subspace here. Okay, so we'll think about that we could be, say, in 3 dimensions here, right? So maybe this is R3, and there's some model which is a 2-dimensional plane. Right, so this is M, and we want it so that the data points in 3D are kind of close to here. Again, we'll assume the data points came from the model and that there's some normal noise that's on, or Gaussian noise on top of these data points. We won't be restricted to R3. 3 dimensions will typically, this is useful in 100 dimensions down to say 2 dimensions, or down to like 5 or 10 dimensions. Okay, and through linear algebra, this will naturally extend to higher dimensions, but this is the problem of, so dimensionality reduction. Dimensionality reduction, right? We think we have too many dimensions. We want to kind of collapse this down to a more manageable number. And then the fifth one we'll talk about is classification. And we'll start with linear classification. With linear classification, again, my data points are in RD, but each xi is in RD, so cross -1, +1, right? And each yi is either a -1 or a +1. It's like a yes or no, a good or bad property. And I'll have a data set, could be in 2 dimensions, and I'm going to have a bunch of, say, some plus points over here, and then I'll have some minus points over here. And the model will be, this model will be a little bit different, the model will be a linear separator of this data. This could be higher dimensions, and something like the probability that the data's label was flipped is somehow depends on the distance from the line, right? So the distance from this line is the probability that we got something wrong about the label. You can do, you can assume something like normal distribution here, but that turns out not to be the right way to solve this problem, but it will be the simplest way to solve all these other problems. Yeah.
What is the formula you put there, say?
Yeah, thank you. Yeah, this is, so times the space of -1 + 1. So there'll be data points in our D, xi, and they'll have a label. The label will be -1 or +1. All right, so don't worry about these details yet. This is, again, just a preview of what we will be doing and kind of an answer to the question, what is a model? It can mean lots of different things. Okay, I kind of want to try and, I'm going to go through this too quickly, and then we're going to review it and go through a more complex example in the next lecture. Okay, but now I want to assume I have 10 minutes left, so let me try and get through this. I think it's a pretty important example here. I assume our data is a subset of R of real values. So let's say, for example, this could be, and we'll call this x1, x2 up to xn. And so I'll write down a concrete example: 1, 3, 12, 5, and 9. This could be heights or something, but I'm just writing up some numbers at this point, okay? And we're going to assume the modeling is that the xi's are drawn from some normal distribution with mean and some sort of standard deviation, okay? That there's some, right, that I've got these values on the line here, and that there's some normal distribution with a mean and a standard deviation, and that those blue data points were drawn from this distribution. So that's the modeling, and my goal is going to be try to recover this value mu, this mean value, okay? I'm going to try and recover the most likely value mu. Okay? I'm going to call this, well, let me just call this m instead of mu, right? So this value m, lowercase m, which will be the most likely model. This is a parameter. I'm parameterizing my model by mu and sigma, and I'm not going to care about sigma. It turns out it won't matter. Okay, but I'm going to care about, so m here, this is my model m is m, and so the space of the models, right, m is also has to be a real number. Okay, so it's the space of models is infinite, right? This is my sample space of models. It's continuous. It could be infinity. It's very unlikely to be, 100 million. That's way outside the range of my data, but I am not ruling it out, right? One thing you could do with the prior here is to say it has to be some range that would rule out things that are infinity, or 100 million, but, it turns out we won't need to do that anyways. Okay, so this normal distribution, let me write down the normal distribution here for m, and let me write down the standard deviation is equal to 2 of a value x. Let me write this as a just function g of x. And so this will be equal to, so we'll assume the standard deviation is 2 just for simplicity. 8 pi, there's some normalization factor here. E to the power, I'll just write exp of a function, because if I put stuff in the exponent, it's hard to tell if it's an exponent or not. So minus 1/8 times m minus x squared. Okay. The 1/8, this came from the choice of the standard deviation is 2. So let me just write down a concrete version of this. Okay, so this gives me the likelihood. What is this? I can think of this guy as the probability in quotes, because it's a PDF, but it's kind of like the probability of that x1 equals to x, given that the parameter m, say that the model equals to m, right? The key parameter of the model is equal to m. Given that choice of m, this is the probability of this data point. So I assume that it came from normal noise, and that means I can write down the probability of the data point given the model, or the likelihood of the data point. I have a probability density function. If I integrate this over x, it integrates to 1. It's a probability density function centered around the value m, right? It looks like that red bump up there. That's a probability distribution. normal noise is a very common assumption of noise. We'll actually see why normal noise. One reason it comes up a lot in the next, we talk about central limit theorem and concentration after this. Okay. But now, because I assume that these are so independent, what I want to write down is something like the probability of the data given the model. And this is going to be the product, okay, just like you write a big sigma, something like a big sigma to do sum, a big pi is like a big product. So I'm taking the product of g of xi. Okay, so these are independent, so that means the probability that I observe all of them is the product of the probabilities of seeing each of them. I can take the product of the individual observations because I assume independence. And I can write down the probability of the data given the model is the product of the likelihoods of each of the probabilities. Again, this is not a probability, it's a likelihood. Okay, it's a PDF here. Okay, and so this is the product of xi and d of, I can write this explicitly, 8 pi x squared. Okay, good. Okay, so I can now write down the probability of the data given the model. This looks, it looks a little bit messy, but I can write this down. If I have a choice of m, given a fixed m, I can calculate this expression. X and xi and m, I can calculate this expression. It's the probability of the data given the model. Assume each data point came from a Gaussian normal distribution with in this case, a standard deviation of 2. Yeah.
Different notation for like the likelihood.
Yeah, we'll get to this on Tuesday. I'm trying not to introduce this all at once. It's a great question, but I'm trying not to do this all at once. Yeah. Okay. So now the important step is we have a few minutes left, so I'm not going to let you go yet. Okay, we are going to maximize this. We want to maximize this expression here, right? So we want to find our goal is to find the argmax m star equals the argmax of m over all the real numbers, right? Of this product now of x. The probability of the data so given the model. Okay, I want to take the argmax of this, right? I want to find the most likely model here. Let me write this as lowercase m just here. Okay, so it's a function of m. D is fixed here, but this is how I'm writing it in that equation up there. And the next trick is going to be cool. Instead, I'm going to look at what's called the log, so likelihood. Okay, so this will be equal to the argmax of m in R of the log of the probability of the data given the model here. Log, when things are the contents are positive, this is a monotonic function. So it's as the value inside the log gets larger, so does the output. So the argmax is the same. The max is not the same, but the argument that maximizes it is the same as it was before without taking the log. Okay, so let me just write down a couple things that what this is going to mean is the argmax of m is going to be the log of pi g of x of xi, and I can decompose the log. Now this is equal to the arg max of m of the sum. I can pull the product outside the log, log of g of xi. Okay. If you know the properties of a log, if you log of a product of two things, it's equal to the sum of the logs of the individual things. So I use that log of a times b is equal to log of a plus log of b. Okay. Then I can say, well, the g is actually an exponent, and if I took the natural log, let's do the natural log here. This will be the arg max of m of the sum of xi, and I can further factor out the coefficient there. So let me do this in two steps as the negative 1/8 m minus xi squared plus this other term, which is going to be xi of the log of the 1 over square root 8 pi. And this term isn't going to matter. It doesn't depend on m. So I can remove that from the argmax. Okay, so now I'm argmax of the negative of the sum of squared distances. Often we take the negative log likelihood and we minimize that. I'm going to minimize the sum of the squared distances. It turns out, and I'm not going to drive this here, this is equal to the average of the set x1 up to xn. If you want to minimize the sum of square distances or maximize the negative of the sum of the square distances to a set of things, the thing that minimizes them is the average of those things. Okay, so the most likely estimate under a noise model, Gaussian, a normal noise model for a set of observations is the average, the mean, the expected value. Okay, so we've derived taking the mean of a point here, of a set of points to get the most likely explanation. Okay, okay, we'll go over this again on Tuesday, go through it a bit more carefully and kind of extend this a little bit. Just let me turn the recording